Okay, this is the last lesson of the series. We're going to work through a few problems together, putting all our new techniques to good use. A pump works in a mine shaft and raises 30 kilograms of water per second from a depth of 5 meters. The water discharges to the surface at a speed of 12 meters a second. 1/5 of the work done by the pump motor overcomes frictional forces. Calculate the power of the motor. You may like to pause the video while you solve the problem for yourself before seeing the solution. Gathering the facts, we have the mass of water pumped per second is equal to 30 kilograms per second. The height or depth that it's pumped is 5 meters. When it arrives at the surface, the water has a speed of 12 meters per second, and we must take note that 1/5 of the total work done is used to overcome friction. The total work done is equal to the change in kinetic energy plus the change in potential energy plus the work done to overcome friction, the non-conservative force. Let's calculate each term separately, then add them all together. We'll calculate the change in energy per second for the kinetic and potential energies because this is the information we're given. For example, 30 kilograms per second. The change in kinetic energy per second equals the final kinetic energy. The water is pumped from rest. Substituting the values, we get an answer of 2,160 joules per second. The change in potential energy per second is equal to the final potential energy because we take the reference level at the original height of the water where h equals 0. The change in potential energy per second equals 1,470 joules per second. The change in mechanical energy per second is 3,630 joules per second. This represents the work done per second on the water to raise it to the surface with a velocity of 12 meters per second. That is 4/5 of the total work done, because 1/5 of this amount of work per second is done on overcoming friction. So the total work done on the water is 5/4 times 3,630, which equals 4,537,5 joules per second. Looking back at the question, we confirm that we must find the power of the pump. The power of the pump is therefore 4,537,5. Let's review the strategy we used to solve that problem. Number 1, we organize the facts. And number 2, we wrote down a formula to help us calculate the total work done by the pump. Looking at the facts, we realized that we were given the mass pumped per second, so we set about calculating the change in the kinetic energy per second, and so on. We did each calculation separately, then added them together to get the change in mechanical energy per second. Finally, we included the work done per second by friction and calculated the total work done per second. And since work done per second is power, we had calculated the power of the pump. Strategy? Keep it simple. Here's the next problem. A constant horizontal force of 10 newtons is needed to drag a box across a rough surface at a constant speed of 5 meters per second. Part A, how much power is used to do this? Part B, how much work is done in 3 minutes? Perhaps you'd like to pause the video while you solve this problem. Take your chance now. Let's write down the facts. The force applied to the box is 10 newtons, and its speed is kept constant at 5 meters per second. Part A asks us to calculate the power. We must choose from these two formulae. Power equals work done divided by time, and the average power equals the force applied times the average velocity. Which one? Well, it'll have to be the second one because the box moves at constant velocity. Let's continue. Part A. P average equals force times V average. Substitute the values and we get an answer of 50 watts. Part B. We need to use the other formula now. Power is the amount of work done divided by time. Multiply 3 minutes by 60 to bring it to seconds. In 3 minutes, 9,000 joules of work is done on the box. And the last problem will be solved first by using principles of dynamics and then by using energy principles. A 5-kilogram block slides from rest for 8 meters down a frictionless inclined plane. The angle of inclination of the plane is 30 degrees to the horizontal. How much work is done on the block by the force of gravity? Pause for a moment and solve the problem using dynamics. You must obviously use the definition of work, but you cannot use energy principles. The work done by gravity is equal to the force due to gravity times the displacement of the block times the cosine of the angle theta between the force due to gravity and the surface of the inclined plane. The angle theta is equal to 60 degrees, as you can see from the diagram. So, work done by gravity equals 5 times g times 8 times cos 60 degrees. The answer, therefore, is 196 joules. Now we solve the same problem using energy principles. What happened to the block in terms of its energy? It moved from a higher position to a lower position. Its potential energy was transferred to kinetic energy. What work did gravity do on the block? It changed the potential energy of the block. So work done by gravity is equal to the change in potential energy of the block. We need to find out how the height of the block above the horizontal surface changed. We know the distance moved is 8 meters along the plane. We also know the plane is inclined at 30 degrees. We can find the change in height using trig. Sine 30 degrees equals change in height divided by 8. Change in height equals 8 times sine 30 degrees. Okay, work done by gravity equals 5 times g times 8 times sine 30 degrees. And the answer, 196 joules. That concludes our series on work, energy, and power. Take care to learn the definitions and statements of laws and the work-energy theorem, and take time practicing further examples. There's no reason why you cannot become an energy expert if you want to.